What specific challenges does your proposed method address in distinguishing between outputs from different LLMs, and why is this important for the field of AI-generated content?
The proposed method addresses the challenge of classifying outputs from different large language models, LLMs, which has been underexplored compared to distinguishing between human and AI-generated content. This is crucial because understanding the unique idiosyncrasies of various LLMs can provide insights into their relative usage, the nature of their training data, and the distinctive features of their outputs. The method demonstrates that classifiers can achieve high accuracy in identifying LLM outputs, even when controlling for factors like output length and format, indicating that LLMs possess inherent characteristics that can be reliably detected. Additionally, the ability to differentiate between outputs from the same model family, albeit with lower accuracy, highlights the nuanced differences that exist even among closely related models. This understanding is vital for applications such as assessing model similarities, ensuring the integrity of AI-generated content, and guiding the responsible use of synthetic data in training.
How does your proposed method work? Please walk through the steps of your framework, including any unique components or algorithms that you have introduced.
Our proposed method involves a synthetic classification task designed to differentiate outputs from various large language models, LLMs. First, we sample a large number of text outputs from each LLM using the same set of prompts, creating distinct output datasets for each model. We then fine-tune a sequence embedding model, specifically LLM2vec, with a classification head to predict which LLM generated each output. The classification performance serves as a measure of the idiosyncrasies present in the LLMs, with our classifiers achieving high accuracy rates, such as 97.1% for chat APIs. Additionally, we analyze the contributions of various factors, including word distribution, markdown formatting, and semantic meaning, to understand the unique characteristics of each LLM's outputs, thereby providing insights into their distinctiveness.
Can you illustrate the inner workings of your classification algorithm with a simple example, detailing the inputs, outputs, and decision-making process?
Our classification algorithm operates by taking text outputs generated by different LLMs as inputs and predicting which model produced each output. For instance, consider a scenario where we have outputs from ChatGPT, Claude, and Grok based on the same prompt. The input to the classifier consists of these text sequences, which are then processed through a fine-tuned sequence embedding model, LLM2vec, that transforms the text into numerical representations. The classifier, structured as a multi-class classification head, analyzes these embeddings to identify distinctive features unique to each LLM. The decision-making process involves comparing the embeddings of the input texts against learned patterns from the training data, ultimately outputting the predicted model for each text, achieving high accuracy levels, such as 97.1% in our experiments.
What experimental setup did you use to validate the effectiveness of your method, including the datasets and metrics employed? How did these experiments demonstrate the method's robustness?
To validate the effectiveness of our method, we constructed a synthetic classification task where we classified outputs from various LLMs, specifically focusing on three groups: chat APIs, instruct LLMs, and base LLMs. We generated 11,000 text sequences for each model using a diverse set of prompts, splitting them into 10,000 for training and 1,000 for validation. The classification performance was measured using accuracy metrics, with our classifiers achieving over 90% accuracy in binary classification tasks and maintaining at least 87.3% accuracy in more challenging N-way classification tasks across different model families. Additionally, we tested the classifier's generalization capabilities by evaluating them on out-of-distribution responses from diverse datasets, which demonstrated robust performance, indicating that the classifiers learn transferable patterns rather than overfitting to specific training data. The experiments also included controlled interventions, such as prompt modifications and text transformations, which consistently yielded high classification accuracy, further underscoring the method's robustness in identifying idiosyncrasies across LLM outputs.
What were the key results of your experiments, and how do these results support the hypothesis that LLMs exhibit idiosyncratic behaviors in their outputs?
The key results of our experiments demonstrate that classifiers can achieve remarkably high accuracy in distinguishing outputs from different LLMs, with a peak of 97.1% accuracy on a 5-way classification task involving models like ChatGPT, Claude, Grok, Gemini, and DeepSeek. This high classification performance indicates the presence of unique idiosyncrasies in LLM outputs, as outputs from different models are not drawn from the same distribution. Additionally, we found that even when controlling for output length and format, the classifiers maintained high accuracy, suggesting that LLM characteristics are deeply embedded in the generated text. Our analysis revealed that distinctive features, such as specific word distributions and markdown formatting, contribute significantly to these idiosyncrasies, as evidenced by minimal declines in accuracy when word order was shuffled. Furthermore, the classifiers demonstrated strong generalization capabilities, maintaining robust performance even on out-of-distribution responses, further supporting the hypothesis that LLMs exhibit unique and identifiable behaviors in their outputs.
What limitations did you encounter with your proposed approach, and how might these impact the applicability of your findings in real-world scenarios?
One limitation encountered in our approach is the relatively low classification accuracy when distinguishing outputs from the same LLM using different sampling strategies, which only achieved slightly above chance levels, e.g., 59% accuracy. This suggests that while LLMs exhibit idiosyncrasies, their outputs can be quite similar when generated under varying conditions, potentially complicating real-world applications where sampling methods may differ. Additionally, the classifiers demonstrated a drop in performance when classifying summarized texts, indicating that semantic transformations can obscure unique characteristics, which may limit the robustness of our findings in practical scenarios. Furthermore, the reliance on synthetic data for training LLMs can propagate idiosyncrasies, as shown by the significant reduction in classification accuracy when fine-tuning models on the same synthetic dataset. These factors highlight the need for careful consideration of output generation conditions and training data diversity when applying our findings to real-world LLM applications.